Hey everyone, welcome back. In my last video, I showed you how I fine-tuned LLaMA 3.1 8B using LoRa inside Kaggle for free. Today, I'll take it one step further. We will run inference using the fine-tuned model, and finally, I will show you how to merge the LoRa adapters with the base model so you can get a complete standalone model. Before diving into the code, first I'll make you understand the concepts with visualization.
Alright, let's understand the first method, LoRa inference. Look at this diagram carefully. Here we have our LLaMA 3.1 8B base model. It's about 16 GB in size. And here are our fine-tuned LoRa adapters. Notice they are only 450 MB. That's 35 times smaller than the base model. During inference, we load both of them together into memory. The base model stays frozen. We don't modify it at all. The LoRa adapter just sits on top and adds its learned behavior. Think of it like the base model is like a car engine and the LoRa adapter is like a performance chip. You plug in the chip and suddenly your car has different characteristics, but you have not actually modified the engine itself. The beauty of this approach, you can have one base model and multiple adapters. Want a base model for customer service, load adapter, need code generation, swap to another adapter. So same base model but have different behaviors. Now let's talk about pros and cons quickly. So advantages are space efficient, only 450 MB per adapter, can switch between different tasks easily, perfect for experimentations. So disadvantages are slightly slower, about 5 to 10% performance overhead, needs the PEFT library, a bit more complex to set up. Now let's look at method 2, merging LoRa adapters with the base model. This is completely different. Again, we start with the base model at 16 GB and our LoRa adapters at 450 MB. But watch what happens. We merge them together. The result, a single unified model. The adapter weights are mathematically added to the base model weights. It's like baking a cake. Once you mix the ingredients and bake it, you can't separate them again. When we merge, we permanently combining the knowledge from both. The LoRa adapters weights gets added to the corresponding layers in the base model. The final model is about 16 GB, the same size as the base model because we are just updating those weights, not adding extra layers. The big advantage, this merge model is now standalone. You don't need PEFT, you don't need to load the two separate files. It works like regular model. Now let's discuss about pros and cons. Faster inference speed, no overhead, simple deployment, just one file, works with any framework production ready. Here the disadvantages are takes up 16 GB per model, can't switch between adapters. If you have 5 different tasks, you need 5 separate 16 GB models. So when should you use LoRa inference? When you are still experimenting, when you have limited storage, when you need multiple adapters for different tasks, during deployment and research phase, and when should you merge? When you are ready for production, when you need maximum speed, when you want simple deployment, when your model is finalized and you are distributing it. Let me show you this comparison table quickly. In speed, merged model wins, it's the fastest. In storage, LoRa inference wins, only 450 MB. In deployment, merged is simpler. In flexibility, LoRa inference is more flexible. So there is no best method. It depends on your use case. Alright, enough theory. Let's jump into the actual code for both methods. Here I am using the Kaggle notebook, and in the model section I provided my fine-tuned LoRa adapters, and same here I am using two T4 GPUs. Let's try LoRa inference. Note in the visualization earlier I shown the base model loaded normally. But here in the code, I am loading the base model in a quantized way for faster and more memory efficient inference. Now let's start by installing the required libraries. I am using TRL for supervised fine-tuning utilities, PEFT for parameter efficient tuning with LoRa, bits and bytes for quantized model loading. So for base model I am using bits and bytes so that I can load it in 4-bit, and transformers is main libraries for model and tokenizer. Next, I import all the important packages, PyTorch, Hugging Face libraries, PEFT, and the tokenizer or model classes. This will be useful for both inference and merging later on. Here, I set the path to my fine-tune checkpoint inside Kaggle. This is where my adapter weights are stored from the training step we did earlier. So here's the path of my fine-tuned adapters. So this path I am providing here. After this, I am logging into the Hugging Face so that I can push the merged model onto Hugging Face hub for inference it later. Now I have defined a helper function to load the model and tokenizer. I used a bits and byte configuration so that I can load the model in 4-bit quantization. That way, the 8 billion model can fit comfortably on the GPU. I also set the pad token to the EOS because casual LMs don't have a separate pad token. Finally, I return the model and the tokenizer. So here I am calling this helper function. Now I have loaded my model and the tokenizer. And this small function just formats the user query into the same cat template that the model was trained on. This generate response helper function takes in a user query, format it, tokenize it, and generates a response with set of generation parameters like temperature, top K, repetition penalty, and max tokens. These control how creative or deterministic the model's output are. Finally, I decode the output and print how long inference took. So let me execute this cell, and so here I am passing the user input as what inspires your choice of travel destinations. So here I am inspired by places that offer a mix of history, natural beauty, and opportunities for unique cultural experience. So this is the response. Now that we understand the inference part, let's move on and merge the LoRa adapters with the base model. Here I have set the three paths: the base model path, the adapter checkpoint path, and the final folder where the merged model will be saved. This cell loads the base model in FP60 precision, and now you might be wondering why are not we using quantized model here during the merging process. Here's why: to merge LoRa adapters with the base model, both need to be in same precision format, typically 16-bit. Even if you start with a quantized 4-bit model, you need to dequantize it to 16-bit first, merge two adapters, and then you can quantize it back to 4-bit afterwards. So the merging itself always happen in full precision. However, once you have created your merged model, you can definitely quantize it again for inference. This gives you a standalone 4 to 8 GB model that's fast and does not need the PEFT library. So the workflow is LoRa plus fully precision base model, and then we are merging it, and finally we are quantizing it. So this is actually a great option for production deployment when you want a single compressed model file. We are attaching the LoRa adapters with the base model and then calling merge and unload that fuses the LoRa weights directly into the base model. Then I save the merged model and tokenizer into a new folder. After this step, the model is fully standalone. No adapter files is required. So I am executing this cell. So the process is started. Standalone model is ready and we can use this for deployment. Now here is our standalone fine-tuned model. Now let's try to inference final merged model. So I am providing this model path here and I am executing these helper methods. So we will inference it in the same manner as we were doing earlier. So in the same way, I am loading the model and its tokenizer. Now model is loaded into the GPU memory and let's try to ask one question. So here is one user input. So the model is responding.
And that's it. Now you know both methods to use your fine-tuned LoRa adapters. And quick recap is in LoRa inference, we keep base model and adapters separate and it's flexible but slightly slower. And in merging, we combine the base model and adapters into one standalone model. It's fast but it takes more space. So for most of you starting out, I had recommend try using LoRa inference first. It's more flexible during the learning phase. Once you are ready to deploy, then merge it. If this helped you, smash that like button, subscribe for more AI content and drop your question in the comment below. See you in the next video.